Hello and welcome to ENGR 330 Fluid Mechanics, the recitation on Chapter 1. What recitation means is we're going to look at some problems from several topics in Chapter 1 and we'll look at step-by-step solutions of those. Okay, let's look at the first problem. If V is a velocity, L a length, and nu a fluid property which is known as the kinematic viscosity and which has the dimensions of L square t to the negative 1, which of the following combinations are dimensionless? So we're given A, B, C, D, we're given several combinations, we have to find which of those combinations are dimensionless. So first we have to know what is dimensionless. So if a particular quantity is dimensionless, then we expect that there would not be any length units nor time units. So if you talk about dimensions, L will be raised to the power 0, T has to be raised to the power 0. And we know that for the problem V is velocity, so its dimensions would be some length scale over time, or L t to the negative 1, and for the little l, lowercase l, the dimensions would be some length, so L, and for the kinematic viscosity, we are given that the dimensions are L square t to the negative 1. So let's look at part A. So we are asked to check if the combination which is V times L times nu, is it dimensionless? So the way we do is, we already know what dimensions of each quantity are, so we just substitute them. L to the negative 1 for the velocity, L for the length, and L square t to the negative 1 for the kinematic viscosity. And if you do the math, you should know the rules of exponents. So it should be L raised to the power 4 t to the negative 2. So you see that it has some dimension. Okay, so our answer is part A is not dimensionless. Okay, because it still has L raised to some power and T raised to some power. Okay, so similarly for part B, which is V L over nu. Okay, so in terms of dimensions, we put L t to the negative 1 times L for the dimensions of the length, and for the kinematic viscosity, you'll see that this will end up to be L power 0, T power 0. Okay, so this quantity is indeed dimensionless. And later on in the course, this becomes a really important number known as the Reynolds number. Okay, all right, so similarly you can do for part C, V square times nu. So I'll let you do it here. So L t to the negative 1 raised to the power 2 L square t to the negative 1. Again, you have to do a little bit of algebra here. So L square t to the negative 2, L square t to the negative 1. Simplify it, you'll end up with L power 4 t to the negative 3. Again, you see that it has dimensions. So it's again not dimensionless. Okay. Similarly, for part D, the combination is V over L nu. So you can see that L t to the negative 1 over L times L square t to the negative 1. So this turns out to be L to the negative 2. Again, since it has some units of length here, it's not dimensionless. Okay, so only part B, which is a combination of VL over mu, which we said would be the Reynolds number, is dimensionless. Okay, so this is how you do this problem, and you realize that I'm using an equal to sign with a dot like this on the top, just to indicate that these two quantities are not really equal to each other. What I'm talking about is the dimensions of this particular quantity. So this is the kind of convention which is shown in your book as well. Okay, so let's move on then to the next problem. This is again a similar problem to what we have done before. Let's see what the variation is. If v is a velocity, you're asked to determine the dimensions of z, alpha, and g, which appear in the dimensionally homogeneous equation as shown. So you have to know what exactly is dimensionally homogeneous equation. So any equation is dimensionally homogeneous if both the left hand side of the equation and the right hand side of the equation have the same units. And also it is important to note that any quantities which are added like this should also have the same units as the left hand side here. So I expect that G should have the same units as V, since we are told it's dimensionally homogeneous, so G will have the units of velocity. Okay, let's do this. So you know that V has the dimensions L t to the negative 1, and if you want you can simplify the above equation as V equals Z alpha minus Z plus G. Okay, and we said for a dimensionally homogeneous equation, each term in the equation should have same dimensions as V, right? So that would mean Z and Z will have the dimensions of velocity, which is L t to the negative 1, and alpha, which is multiplying Z, since already Z has the units of L t to the negative 1, which is the units of velocity, alpha has to be dimensionless. Okay, so alpha is a dimensionless quantity. Okay, alright, so that's how you do this particular problem. The key thing here is you learned what exactly is a dimensionally homogeneous equation. Okay, let's go on to another problem. The information on a can of pop indicates that the can contains 355 milliliters. So what you're given is the volume, okay? And you should be able to realize those from the units given. The mass of a full can of pop is 0.369 kilograms, while an empty can weighs 0.153 newtons. Again, realize that in one case you're given mass, in one case you're given weight. Okay, you're asked to determine the specific weight, the density, and specific gravity of the pop and compare your results with the corresponding values for water at 20 C, and you're asked to express your results in SI units. Okay, first let's define what is specific gravity, or first let's define what is specific weight, since that's the first thing we have to find. So specific weight of a fluid gamma is defined as rho, or the density of the fluid, times acceleration due to gravity. Okay. Okay. And I know that we are given volume of fluid, right? And I can also figure out a way of finding the weight of the fluid, right? So what at this point, what I'm going to do is I'm going to write rho fluid times z multiplied by mass of the fluid, and then I'm going to divide by the same quantity. So I'm not really changing anything, I'm just doing this. And the reason I'm doing this is, you'll see it in a bit here. You know that this guy then becomes the weight of fluid, right? And then you can further simplify this. So weight of fluid, and then what I'm going to do is I'm going to take this density of the fluid into the denominator. Okay. Well, so that's what you got, but you also know that density of the fluid is actually defined as mass of the fluid divided by the volume of the fluid. Okay, so we're gonna try to use all of this information and then put them in the problem. So the first thing in this case is, how do we find the weight of the fluid? Okay, so this guy here, for example, first let's confirm this. So this quantity here, from what I have written here, I can write this guy as volume of fluid. Okay. Okay, so what I can do is, the specific weight of the fluid will then be, I'm going to write weight of fluid divided by the volume of fluid. Okay, so how can we find the weight of the fluid? We have information here. We know what a full can mass is, while an empty can weighs so much. So we can use that fact. So this would be 0.369, which is the mass of a full can, times acceleration due to gravity, which is what we are given there, right? 0.369 minus mass, or in this case it should be the weight of an empty can. So that gives us the weight of the fluid essentially in the can. So 0.153 divided by the volume of the fluid. I want to have everything in SI units, so I'm going to convert milliliters to liters. So this is what I end up with. So if you put in the numbers, this will be 9766 Newton per meter cube. Okay. So once you know the specific weight, you can just list it, since that's your answer. And you're also asked to find the density of the fluid at this point. Since you know the specific weight, the density would be the specific weight over the acceleration due to gravity. In SI units, it would be 995 kilograms per meter cube. And then finally, the specific gravity of the fluid, which is defined as the density of the fluid over density of water at 4 degrees C. So we just found the density of the fluid divided by density of water at 1000 degrees, sorry, at 4 degrees C, which is 1000 kilogram per meter cube. So you know that you're dividing the same quantity, so the units cancel out. So this is the dimensionless quantity. So it's about 0.995. And then at the end, you're asked to compare these results with water at 20 degrees C. So this is table B2. Okay, I just pulled off at 20 degrees C. What exactly are these values? You can see that the density of water is given here, the specific weight is given, and you can find out the specific gravity from here, and you can see that all of them are higher than for your pop. Okay, and if you're wondering, since this really doesn't have the specific gravity, you can calculate it. So let me write specific gravity here is 0.9982, and you'll see that all of them are, all these values are higher than what we just computed. Okay, and realize that the unit here is 9.789 kilonewton per meter cube. So if you take out the kilo and multiply it here, it's 9789, which is greater than 9766 newton per meter cube. So make sure what is given in these tables, are they talking about kilonewton per meter cube or just newton per meter cube? Okay, that makes a big difference. So get used to those. Okay, so that's what it is for this particular problem. Let's move on to the next one now. So a helium-filled blimp, as shown in this figure, is used at several athletic events. We're asked to determine the number of pounds of helium within it if its volume is 68,000 cubic feet and the temperature and pressure are 80 degrees Fahrenheit and the pressure is 14.2 pounds per square inch, and A denotes its absolute. Okay? So at this point you have to realize that helium is an ideal gas. So I can write the ideal gas law, which says the absolute pressure is equal to the density of helium times the gas constant times the absolute temperature of helium. Okay, so we know the volume, and what we are asked to find is what is mass of helium in this problem. So we know everything else. We can find helium from the tables. R for helium is 1.242 into 10 to the 4 foot times pound per slug Rankine. And then since these units are in Rankine, which is an absolute scale in English system, you should convert the temperature, which is in 80F, to the Rankine scale. Okay, and I'll let you look at this. It's a simple addition of a number to your Fahrenheit scale. So that's what it is, and we know the pressure here, we know the volume. Okay, so now we can write the density. So the pressure will be equals to, and then I'm going to write the density as mass of helium over volume of helium times R and T, which we found in the previous slide. So from here I can then write mass of helium is pressure times volume over R times T. Okay, so your final answer should be 668 pounds. Okay, and it's not that it's that simple. You just have to make sure you convert everything in the right units and see if you get this answer. So that's a good exercise for you guys. Okay, so let's move on to the next problem. Okay, a 25 diameter shaft is pulled through a cylindrical bearing as shown in this figure. The lubricant that fills the 0.3 gap between the shaft and the bearing is an oil which has the kinematic viscosity as mentioned here and has a specific gravity of 0.91. We're asked to determine the force P required to pull the shaft at a velocity of 3 meters per second. And you're asked to assume that the velocity distribution in the gap is linear. Okay? Okay, let's see what are the forces which actually act, which are acting on this particular system. So if you draw for the shaft, so the forces which are acting on the shaft is the force which is pulling it, and then you have the shear stress here, and it's not a force, but you can multiply with an area and then that becomes a force. Okay, so and if I denote this to be my positive x direction, sum of the forces acting, which is sigma fx, should be equal to 0, which means P equals the shear stress times the area. Okay, so area here A will be pi times d, because we are talking about a cylindrical shaft, and times the length of the shaft which is in the bearing. Okay, and we are talking about this length here, which is 0.5 meters. Okay, so that's, so this guy, I should make a note, is 0.5 meters. Okay, so now we can use the fact that equation 1.9 gives shear stress is equal to mu du dy. Since the velocity is linear, it would satisfy no slip condition at the wall. So this will be mu times v shaft velocity, which we are given, divided by the gap, which is 0.3 and later on we'll convert this to meters. Okay, and also the kinematic viscosity is the absolute viscosity divided by the density of oil. Okay, and the specific gravity is the density of oil over density of water at 4 degrees C. So this is 0.91. Okay, so then we can find density of oil, which will be 910 kilograms per meter cube. So that will then give us the absolute viscosity, okay, so which would be the kinematic viscosity, which we know, and we just calculated the density. So the absolute viscosity will be 0.728 kilogram per meter second. And then you can substitute this in here and make the corresponding unit conversions. Then you'll get tau to be 7280 Newton per meter square. Okay, and you can always calculate the area, pi times d. Okay, I'm converting them into meters, times the length of the shaft in the bearing, which is 0.5 meters. So this turns out to be 0.0393 square meters. So the pressure is nothing but the shear stress times area, which we want. This would be about 286 newtons. Okay. So all we had to do here was to find the absolute viscosity and use the shear stress formula. Okay, let's look at another problem. A layer of water flows down an inclined fixed surface with the velocity profile shown in here. You're asked to determine the magnitude and the direction of the shearing stress that the water exerts on the fixed surface for velocity equals 2 meters per second and h equals 0.1 meters. Okay, again, we can use the fact which we used before, that shear stress will be equal to mu du dy, right? So we know the velocity profile which is given in the figure, so I can then find du dy, okay, and we can do this. It's a simple derivative, so this is what you end up with. Okay, then you're asked to evaluate these at a fixed surface, so you want to find du dy at y equals 0 fixed surface, so which is 2u over h. Okay, and you're then asked to find the shear stress, so we just computed du dy at y equals 0, so it will be, shear stress will be mu times 2u over h. Okay, so you can then put the values for the viscosity, absolute viscosity, unless it is otherwise mentioned. If you're not given any temperature, just use what is in the front of the book for water in the corresponding units. Here we are talking about SI units, so just go to that particular column. So times 2 times the velocity, which is 2 meters per second, so times 2 divided by the height, which is 0.1 meters, which is given in the problem, right? So if you do the math here, you'll end up with 0.0448 Newton per meter square, and since it is shear stress, it will be force per area, so that's why you have Newton per meter square, and this acts in the direction of the flow. Okay, all right, let's go on to the next problem. So oxygen at 30 degrees Celsius and 300 kilopascals absolute pressure expands isothermally to an absolute pressure of 120 kilopascals, and you're asked to determine the final density of gas. So in this case, we want to know what is an isothermal process. So if you have taken thermodynamics, you know that isothermal process is a process where temperature, which is one of the properties, remains constant. So isothermal implies T is constant. Okay, so oxygen can be treated as an ideal gas. So P in general will be equal to rho R T, but since T is constant, I have P over rho, and R is a constant, so P over rho is a constant. Okay, and if I call the two states as initial and final, right, and let me say one denotes initial, two denotes final. So I can then write P1 over row 1 is equal to P2 over row 2, which implies row 2 is P2 row 1 or row initial over P initial. Okay. So in this case, you know P final, you know P initial. You don't really know row 1, but you can find it, right? You can always convert it using the ideal gas. Okay, so let me write here. So I know P2 is 120 kilopascals, P initial is 300 kilopascals, and row 1 is P1 over R P1. So just substitute the corresponding numbers and make sure P is in absolute scale. So you'll get row 1 to be 3.81 kg per meter cube. And then once you know that, you can then find row 2. So row 2 will be 120 over 300, which is P final over P initial or P2 over P1 times the density which we just found, the initial density. So you'll end up with 1.52 kg per meter cube. Okay. All right. Let's look at this interesting problem. During a mountain climbing trip, it is observed that the water used to cook a meal boils at 90 degrees C rather than the standard 100 degrees C at sea level. At what altitude are the climbers preparing their meal? And we are suggested to look at a couple of tables to solve this problem. So here we have to know the fact that as the water begins to boil, the pressure boiling will be equal to the vapor pressure. Okay, so this comes from the fact that you've learned vapor pressure here. So from table B2 B2 here, the for 90 degrees C, the corresponding vapor pressure is 7 times 10 to the 4 Newton per meter square absolute. Okay. Then go to table C2, which gives the properties of US standard atmospheric pressure, atmosphere as a change in altitude, and I just picked out for our pressure, which is the same here, what would be the altitude, and it happens to be 3000 meters. So the answer is pretty simple here. So the altitude is 3000 meters. Okay, and and this is the reason why as you go up in altitude, your pressure drops, and also your boiling point as well drops. Okay. Okay, let's look at one last problem in this chapter, which will talk about surface tension. Okay. Okay, so what we have here is a water strider bug is supported on a surface of a pond by surface tension acting along an interface between the water and the bug's legs, okay, as shown here. You're asked to determine the minimum length of this interface, which is this guy here, this interface between the water and the bug's leg. Oh, sorry. Determine the minimum length of this interface needed to support the bug. You're asked to assume the bug weighs 10 to the negative 4 newtons and the surface tension force acts vertically upwards, and you're asked to repeat Part A, the surface tension were to support a person weighing 750 newtons. Okay. So again, we would ideally would like to know the forces involved in this particular problem. So if I try to recreate this bug here, so we know that the surface tension is acting in this direction, it's pulling, right? So it's surface tension, but if you want to write it as a force, you need to multiply with the length. The surface tension has a unit of force per length, so this then gives us a force, and then there is the weight of the bug itself. Okay, so if I consider this as my y direction, sigma Fy should be 0 for equilibrium. Okay, so that means W will be equal to sigma L. Okay, that's pretty straightforward. So part A, you're asked to find this length of that interface. So L will be W over sigma. You know these values, you know the weight of the bug, and the surface tension, you can find this from the tables, 7.34 10 to the negative 2 Newton per meter. So this would be about 1.36 mm. So you can see that it's pretty thin. Whereas if you do the same thing for a person weighing 750 newtons divided by sigma, you'll see that this is about 10.2 kilometers or 6.34 miles. Okay, the reason I'm showing two units is I just want you to check it and see if you're able to convert from one or the other. Anyway, so you can see that as the weight increases, this length has become really gigantic. Okay, so it's not really possible. Anyway, so this concludes the session, recitation or problem solving for chapter 1. We'll talk to you pretty soon. Good luck.